Okay, so as promised, this lecture we're going to continue on compact spaces. So last time we introduced some definition and basic properties of compact spaces. So let's just list them here and we skip the proofs because we did it in the last time. So first definition, a space is to be compact if for any open cover there is a finite subcover that covers X. And note that it is a topological property, so well, it's easy to check, so you can check it immediately. And the definition is that Y is a subset of X, and a collection of subset of X covers Y if union sets in A contains Y. And we say that Y is compact, the subspace is compact, if and only if for every covering of Y by open sets in X contains a finite subcollection and also covers Y. And here's some theorems that Y is closed subspace of a compact space is a compact space. Compact subspace of a Hausdorff space is a closed set. And the compact subspace of a Hausdorff space X, we know that from our proof. We have that for any X naught that is not in Y, there exists disjoint U V open set in X such that X naught is in U and Y is contained in V. Okay, so here comes the first theorem for this lecture, is that continuous function on a compact set, then its image is also a compact set. It's a compact space. And the proof is easy. For any covering of fx open in Y, we consider the sets of all the pre-images for every A and the covering, right? We consider all the pre-image. Well, this pre-image is in fact an open cover of X, right? And right? Because it covers fx, right? So this pre-image is an open cover of X. By compactness, finitely of them, X is compact. And if this is open cover of X, then this covers fx. Why? Because, well, if this is open cover of X, which means that for any little x in X, X must be in some, say, AI. Okay? So for any X in some AI, this means that fx is in some AI. But fx is precisely an element in fx. So for any element in fx, it must be in some of the AIs, which means that this, this is contained and any elements in there must be in some of the AIs from 1 to n, right? So here's an important application of this theorem. We have that compact space and Hausdorff space, then if we are bijective and continuous, automatically implies that it is a homeomorphism, given that there's a compact space and this is a Hausdorff space. Well, just check F is a closed map, right? This is all we need to check right now, because, right, we already showed that it's a bijective and the F is continuous. We want to show that this is continuous, right? But with the pre-image definition, right, something like that, which is precisely equal to F of V because F is a bijection, right? So we just checked F is a closed map that brings closed sets to closed sets. Well, this is easy. For any C closed in X is a compact, so C is compact. So F of C is compact. Compact subset of a Hausdorff space is a closed in Y. And here we have a theorem of product of compact sets. The two product of compact set is compact. Okay, so proof. So let's first fix it X naught in X and N open in X times Y, containing X times Y. X naught times Y. Okay, such N always exists if we just pick this itself. So we can just assume there's an open set contains X naught times Y. And here's the claim. The claim states that there exists a neighborhood of X naught and X such that the product is contained entirely in N. Okay? So if we have X naught times Y and an open set contains it, there exists another, right, another neighborhood of x naught such that w times y is in n. And we'd call this a tube about x naught times y. Okay, so to prove the claim, first we cover x naught times y by the basis elements u times v and x times y, and each is lying in n. This is possible because what we want to show that is that we can cover this by basis elements in x times y. So basis elements for the product topology, we have u is open in x and v is open in y, right? Okay. So how come we can do this? We can cover this by basis elements such that each is lying in n. Why can we do this? Because first we take an open cover of n, right? We open cover of n because n is open in x times y, then each set are open in x times y. N is open in x times y, right? We pick n open in x times y. So open cover of n. So each of them are open sets in n. But n is also open in x times y, so each set in A are open in x times y. But we know that each open set in x times y is a union of basis elements that looks like u times v, where u is open in x, v is open in y. So we can say that just an open cover of n with those elements, right? Because each set in here are open x times y, but each open set in x times y is a union of them, right? So the collection is really just a union of a bunch of those, right? Right? Correct. And we know that, okay, each element in A open in n, which means it's contained in n. So those basis elements are, of course, also contained in n, right? So, right? It covers n, right? Open cover of n with those basis elements. N contains x naught times y, so this is also a covering of x naught times y, but it is homeomorphic with y, and y is compact, right? So we can cover it by finally many basis elements. We just assume that they intersects x naught times y, right? We just assume that each of them intersects x naught times y. Otherwise, we don't really care about it, right? We just remove it. We just remove it. If this don't intersect, we remove it, right? Okay, so the rest we assume that this is a collection such that all of them intersects x naught times y. So from here we can just define W to be their intersection. Each is open in x, and that contains x naught. Right? It is open in x because it is a finite intersection of open sets, and it contains x naught. Right? Because each of them contains x naught. So now we can see that, okay, for any x times y and w times y, okay, for any elements in here, for this y, we can consider the corresponding x naught times y. And the corresponding x naught times y is covered by finally of them, so it must be in some ui, vi. This implies that y is in some vi. Okay, so for any x times y and w times y, we have y is in some vi. But x is also in w, but w is in all of the u's, so it must also be in the corresponding ui. Right, so x times y is in ui times vi. So any elements is in some ui times vi, which is as desired. U cross y is contained in n, a finite product, as we claim. Right, there exists a neighborhood of x naught such that x times y is contained in n. Okay, so we call W this. Right, to define this open set, it must be open in x, right? Because only finite intersection is allowed. And reduced to the finite case is by the compactness of y, hence the compactness of x naught times y. See? So this is the importance. So now we show our main claim. We show that it is compact. So first pick an open cover of x times y. For each x naught times y, right, basically it is compact, so we can pick finally of them, right, because it's compact. Now, we define n as the union of them, that is the open set, of course, open in x times y that contains x naught times y. By the claim, we have a 2, right? So we just do this for every x. And this gives our wx. And wx times y is covered by finitely many sets in A. Right, this set is covered by finitely many sets in A. So all the w is an open cover of x, right? So all the wx, of course, like wx is neighborhood of x. If we just run through all the neighborhoods, like this is an open cover of x by compactness, we have finally of them. And each wx1, wxn, okay, from here, okay, from this to this, right, we have x times y is equal to those, but each this is covered by finitely many sets in A, right? So if we take all the unions within is again contained based on finite collection of elements in A, right? This union is again finite elements of A, right? So this is contained in some A, but all those A's are assumed to be contained in this. So in fact, this is equal to some, I don't know, some A, P, right? Yes, exactly. So we have a finite subcover. Okay, so this is the compactness of finite two product, but finite product follows by induction. And here's the lemma we wanna use in the future, is that if y is compact, if n is open and x times y contains this, then there is w neighborhood of x naught such that the tube is contained in it. And a finite case follows by induction and the following homeomorphism. Right, these two spaces are homeomorphic. And in the infinite case, it still holds, but we will do it later, okay? Even in the infinite case, it still holds, and this is important theorem, right? And this will be covered in functional analysis, but I haven't learned it yet. But I know that this is a theorem, like infinite product of compact space is still compact. Okay, so wait, we will do it later. Another criterion for compactness, we're going to do it with closed sets. So first, a definition with closed sets. Given a collection of subsets, we have this collection has a finite intersection property if for any finite subcollection their intersection is non-empty. This is true for any finite subcollection. The intersection is non-zero. So we can characterize compactness with this definition. We say as compact, we have that if and only if for any collection of closed sets such that it has an intersection property, finite intersection property, implies all the elements in the collection, the intersection is non-empty. So this is equivalent to the space X being compact, okay? So for any collection of closed sets that has finite intersection property, such that, right, we have that the intersection for all sets is non-empty. And the proof, so first we need those three facts. So first of all, given a collection of subsets, we define C as the collection of the complements for elements for members in A. Okay, so first, collection and A are open if only if sets in C are closed. I think this should be clear enough. And if A covered X, if only if the intersection is empty. This is by those 2 and 3, right? This is by De Morgan's law. And here's the finite case. If finally uncovered as a finally of them intersection empty. These two are by De Morgan's law, okay? And the first one is by definition. Okay, so we're gonna use these three facts to prove it. So here is the proof. X is compact if and only if by definition for any collection of sets of X, if it covers X, then there's a finite subcollection that covers X. If and only if, so from here to if then we take the contrapositive. For any collection, this is the same. If this is false, implies this is false, right? So equivalent of being saying exists means no finite covers X, then A does not cover X. Now we're going to use 2, right, and 1, and 3, like anything, doesn't matter. This means that for any collection of closed sets, right, if A is a collection of open sets, then for any collection of closed sets, right, if no finite collection such that this covers X means this is empty, right? If no finite collections, so it means that all finite, this is not empty. It's not empty, right? Then A does not cover X means that this is not empty, right? So this implies this is not empty, right? And this is really it. This is precisely our statement here. Precisely our statement here. Okay? So here's a remark. In a special case, if this is a nested sequence and the subsets, so if it's a nested sequence of sets, each is non-empty, then it has a finite intersection property, right? If each of them are non-empty, then it has a finite intersection property. And if each of them is closed and X is compact, this will imply that all the intersections are non-empty, right? Here, all the intersections are non-empty. And we will use those results. And now first, let's come back to the Euclidean space. And the building block for this section in the Euclidean space is to show that the closed intervals in R is compact. So, to show this, given this enclosed interval AB, if A is going to be as trivial, right, because it's a finite set. Finite sets are compact. So let A less than B. Given an arbitrary like open cover, we define as a subset of AB such that it consists of elements such that AX covered by finally many UIs. It is non-empty because A is an S, and you're a subset of AB, so it is bounded above by B. Non-empty subset that is bounded above, we can pick in supremum, least upper bound. First, X must be greater than A. Why? Because A is an open set, so there is an epsilon such that AA plus is once contained in it. Right? So all the elements between A and A plus epsilon is contained by a single element UI naught, which is indeed there in S. So we want to show that X naught is equal to B in order to show that AB can be covered by finite, right? This is what we want. So first we show that X naught is in B, and then we show that B is in S, right? So we first assume X naught is less than B to get a conjugation. We already have it as greater than A, so it must be less than or equal to B. But we assume that it's less than B, we get a contradiction because first we take a UI naught that contains X naught, right? Because it's covered, right? So there exists epsilon such that a little epsilon neighborhood is still contained by this UI naught. But X naught minus epsilon is less than S, right? This is less than the supremum, which means I can find another X1 that is in between them that is contained in S. Well, this means that AX1 is covered by fairly many UIs, right? But A to X naught plus epsilon, right? Remember here, right? So this is covered by those union with UI naught, right? I hope this is clear enough. So S plus epsilon should be an S, right? It is covered by finally many of them. But this is greater than the supremum. So X must be equal to B. There's a contradiction here, right? There's a contradiction here. To show that X naught is an S, similarly, because we can pick epsilon greater than 0 such that it is contained in some UI naught, and again, right? And we can find an X1 that is between them, right? Because this is not in the least upper bound. Right, this is not at least upper bound, we can find another of them. So this union and this is some finite union of UIs, which is our claim. right? This is equal to AB. So AB is a finite union of UIs. So we're done. As we wish, right? So the compact and closed intervals are compact. Okay, so this is everything for this lecture, and next time we're gonna continue. Okay, I'll see you guys next time.